So just a little more background on the multinomial probability function. What the multinomial probability function addresses is, imagine that I generate a large number of prices, and they're all come from a set of given prices, S0 u to the n, S0 u to the n minus 1 d, so forth. And I let nj, as before, equal the number of prices that happen to equal the jth value in my series, which I might just denote as, doesn't matter how I ordered this is easy. The multinomial distribution addresses the probability distribution of the vector n0, n1, up to nn. I have n plus 1 possible outcomes, little n plus 1 possible outcomes, and I generate capital N random variables. Each one of them has to be one of those outcomes. And I know the probability of each one in advance. The probability of nj is given as pj. Well, the multinomial distribution provides the probability for any specific outcome of values that adds up to capital N. Apparently, the sum of all the nj's has to be capital N, what I generate. And what the multinomial distribution theory tells us is that the expected value of any nj is exactly equal to, always, n times the original probability. So it's a generalization of the binomial, as the name multinomial would suggest. It also turns out the variance of any one of these nj's looks like the binomial formula. It's n times pj times 1 minus pj. So what this says is that in this multinomial distribution, every one of the random variables has the same mean and variance as the binomial with the same single parameter. And there's a covariance between any two n's, which is negative, because if one goes up, the other one in general has to come down, because they all have to add up to capital N. So this is really the key point. These other statistics are useful when proving that, in fact, with Chebyshev, this estimation procedure actually converges in probability. This is what motivates the fact that the expected value of my estimated price is the real price. But that's a little bit different than saying that this estimated price actually converges with probability 1. But that's also true. Now, we can do Monte Carlo with real or risk-neutral probabilities. The question here is, can we use real-world P for Monte Carlo? And the answer is yes. The procedure of Monte Carlo is a procedure for generating random variables that have the appropriate probability distribution, and then to use those generated random variables in various applications. Now, we would not want to generate, using a Monte Carlo method, real-world stock prices if our goal was to price options. We know for that application we must generate prices in the risk-neutral measure. However, if we're interested in generating what might the distribution of stock prices be in time 5 years in the real world, and you might be interested in that for capital modeling or other applications related to the balance sheet where you really care about the real world and real world probabilities, then certainly all these same methods work. The difference is we use the real world probability P instead of P star. We use the real world return alpha instead of the risk neutral return R. And when we present value, if we wanted to do this with an option application, and we've seen that we can price options in theory in the real world, but we cannot use the risk-free R, we have to use the real-world return gamma. So Monte Carlo works in the real-world model or in the probability or the risk-neutral model. Can the real-world model and Monte Carlo be used for option pricing? Yes, in theory, but there's a complexity here that's even greater than the complexity we saw in Chapter 10, where we showed that we could, in theory, price an option with real-world probabilities. Namely, the complication is, as we saw in equation 11.6, the return we have to assume is equal to the return on the replicating portfolio of the option. Now, one problem is that we don't know the replicating portfolio until we price the option, and for that we need the risk-neutral. But imagine that we had the risk-neutral pricing and therefore had the replicating portfolio. Gamma, the return we need for real-world pricing, is the return on that replicating portfolio. The complication for Monte Carlo pricing is that the replicating portfolio changes at every node of the lattice. That means that gamma changes at every step in the lattice. Unlike when we use risk-neutral pricing, P we calculate and we can use the same R everywhere. If we want to use Monte Carlo pricing, then for every path of stock prices that we generate, we have to use a different discounting gamma, which reflects the replicating portfolio at each node of the lattice that our path goes through. And this next table shows, so you can see in the first node at time 0, the replicating portfolio implies a gamma of almost 36%. The real-world gamma in this example had a P of around 0.52. But this example from the book, at time 0, the replicating portfolio had a real-world return, given the parameters of the stock price, etc., had a real-world return of 36%. And that would have to be used for the first period in any Monte Carlo method using real-world probabilities. In the second period, it depends on where we end up. Namely, that you can see that in the 3 periods where we went up after the first period, so we ended up at an up state, at that state for the next period, the discount rate was 32.3% in the replicating portfolio. But however, if we went down in the first period, we went to a down state, then it's 49%. So in other words, what we're saying is, here we have our lattice. And for the first period, it's 35.7. If we go up, the second period return is 32.3. If we went down, which we did in the fourth case, it's 49.5. So if you wanted to price an option using Monte Carlo, you would have to remember that although everything works the same in terms of generating stock prices with alpha, generating payoffs, that's all fine. But the discount factor for every payoff has to reflect the path taken to get to that payoff.